Okay. So in this section, we would discuss about spatial information science, data acquisition, accuracy, precision, and errors. So it's an interesting aspect of spatial information as we are dealing with digital data. So these characteristic of digital data where we would be importing the data from different sources, that is data acquisition. The data's accuracy is very important. The precision, the resolution of the data, that is also important. And all of them, if they are not at appropriate consistency, then there might be certain errors. So in this section, we would be highlighting these issues related with spatial information science. The power of spatial information science exists in its ability to use many types of data related to the same geographical area, integrating different data sets within a single system and perform the analysis. Some common sources of error in spatial information science data include incomplete or outdated data sources, errors in data during entry while importing the data into the information system, or conversion while we are converting the format. As you know that we can import the data in different formats. So while importing, while we change the formats, there might be certain errors which may come during the conversion of data to appropriate format which is applicable for the software which we might be using. Then imprecise or inaccurate measurements and certain inherent limitations of the data collection method. These are some of the ways through which we can which result into some kind of errors in spatial information. Accuracy and precision are both important aspects of GIS data, its quality, but they refer to different things. In order to really understand the relevance of accuracy and precision, we need to understand the difference between both terms. The first is accuracy. It can be defined as the degree of closeness to which the information on a map matches the values in the real world. Therefore, when we refer to accuracy, we are talking about quality of the data and about number of errors contained in certain data sets. In spatial information science data, accuracy can be referred to a geographic position, but it can be referred also to attribute or even conceptual accuracy. Precision refers how exact is the description of data. Precise data may be inaccurate because it may be exactly described but inaccurately gathered. Maybe the data collector made a mistake or the data was recorded wrongly into the database. So, error involves assessing both the imprecision of data and its inaccuracies. Now, errors in data may derive from three main sources. They are, first, errors in the sources of data. It may be the error in maps used by surveyor or printing errors. This is one way of errors which might be coming along with the data. While the second can be errors while encoding. It may be, for example, scanning errors, digitizing errors, typing errors. These are some common methods, ways through which errors may come while we are encoding the data into spatial information science. Then errors at the time of transfer or conversion. While transferring and converting the data, as we are saying that there are different formats, in this process also errors may come. And also in some cases the data may lost also during the course of transfer and conversion. So this data loss and conversion of different data formats, both of them in some way bring some kind of error into the spatial information. So begin with the scale of spatial data and age of spatial information data both brings inherent error in mapping. For example, an inherent error in cartography depends on any discrepancy in scale used for map preparation. That may be one reason. And we represent different type of data in different quantity and with different quality or for different purposes also. As map maker, we always adapt the scale of work to the level of detail needed in the projects. Similarly, if data sources are too old, some or greater part of the information base have been changed. So this kind of old data and the lack of currency brings error for contemporary analysis. So this way also the data is not up to date, and in some way we can say that data has some kind of error. The scale of spatial data example is very clearly can be seen in this particular image which is depicted, which is presented before you. So errors in input data may derive from three main sources, as we have seen. They are errors in the source of data. It may be the errors in maps used by due to printing errors during encoding, and errors at the time of transfer and conversion, as we have seen. So you see, in this kind of errors, it result into spatial information science data formatting errors. These are some types of errors created while formatting data for processing, where there might be changes in the scale, the reprojections, and import-export of raster to vector. So there the data format is changing. These are possible sources of formatting errors. You can see in this image also, which is presented before you. Now this can be rectified, and this process is known as the rubber sheeting. Then another important type of error, I would say, is the attribute errors. So we all know that in spatial information there is also attribute information linked to the spatial information. So attribute data may also have some errors, but it could be identified easily by manual methods and we can compare with the original data. These errors can be quantitative as well as qualitative errors also. It can be both with improper labeling. For instance, an agricultural land may be incorrectly marked as forest area. So this is one attributional error where we are posting it differently, wrongly. And this would cause an error that the map user may not notice because they may not be familiar with the terrain, the area in question. The second kind of attribute error can be the quantitative error. It may occur if instrument or source of information that may not have been properly calibrated, checked. This may result into some kind of errors. This leads to aggravating subsequent errors, which is hard to identify in the field, but that will cause project to lose accuracy and reliability. So these attributional errors, they also contribute a lot, and we need to take care of these errors also. There are many methods for checking and correcting attribute data. Some of them are like impossible value. We could check the error value when we know the range of data, and if it goes beyond the range, then obviously we can think that there is some kind of errors which might be existing in the data. So that way we can rectify it. There can be extreme values also. We can again identify the errors in data by extreme values. The another can be the inherent internal consistency. By tallying, we could check the error in total and averages, something like that. A good example could be the scatter diagram. The error in correlation of two attribute data could be identified using scatter diagrams also. Another can be the trend surface. It will highlight the point which have a long range from other figures. So these are some obvious ways through which attribute related data can be rectified. Then another kind of errors that may be called as positional accuracy. Positional accuracy is the quantifiable value that represents the positional difference between two geospatial layers, or between a geospatial layer and the ground reality. An example for this is the comparison of the location of roads in a feature class versus their location in any TIFF image, for example, or JPEG image, for example. If the feature class and the TIFF are used the same projection, you can assess the positional difference between the feature class and the image which is being incorporated into spatial information. The positional accuracy assessment tool, commonly known as PAAT, P-A-A-T, allows us to compare two items to assess a data layer's accuracy in relation to a reference layer of known or unknown accuracy. Now, another kind of error which is very common but it plays a very important role in spatial information science, the topology, the topological errors. As you are now aware, we have discussed earlier also, that topology defines and enforces data integrity rules. Simply it means there should be no gaps between polygons or different entities which we are representing through the spatial information. It can, I'm emphasizing on polygons because the topology is more concerned with the polygons, but it is also concerned with point and line entity also. So the arrangement of point, line, area entity, it has some specific orientation, and if there is some kind of discrepancy in the arrangement of these spatial entities, that refers to topological errors. So topological errors occur when data is, for example, scanned or even digitized, and there are some errors which are coming into the digitizing or scanning process, within the digitizing and scanning process. They are mostly the result of human error or might be the computer error or the device error which may result into topological error. They can also occur when raster data is turned into vector data. We have seen this example earlier, that when we convert the data from raster to vector or vector to raster, the conversion process has some inherent flaws and that result into some kind of errors. In both the cases, whether we transform the data from raster to vector or to vector to raster, in both these cases, the lines, vector lines or raster pixels are created must be required to process to form topological correct relationship, especially when we create polygons. Some examples of this include, as it is being depicted in this image which is presented before you, the common examples are overshoot or undershoot. The sliver polygons, we have discussed these errors earlier also. So I'm not going into the detail, but the image itself gives you an idea as to what kind of errors may come due to topological errors. The undisclosed and unclosed polygons and mismatching adjacent polygons. These are some of the errors which you might see because of topological errors. Especially vector data editing errors may occur in vector data also. These errors are mainly because of digitizing process. Because we would be digitizing in the form of, for example, as shape files. The topological errors may also dealt with raster data editing. The spatial data error creates more problems and it is difficult to identify. In raster data editing refers to correcting specific contents of raster images than their general characteristics. Commonly used raster data editing functions are, for example, filling holes and gaps. It used to fill holes and gaps appear in raster images. You can see in the top row example. Another can be edge smoothing and boundary simplification. Here we would be removing and filling single pixel irregularities along the line edges. Another could be de-squeam. It is used to rotate the image. Another can be speckle removal or filtering, to remove the speckles or random highs or low valued pixels in the image. Another can be erase or delete. Here we would be removing the unwanted pixels. You see the examples very clearly. It is visible as to how the raster data, topological raster data is corrected. So these are errors which comes into the raster topological data. Another can be thinning, to reduce the representation of linear features to single cell width. It is done to preserve sharp corners and round corners. And this example we have again seen in our previous sessions. Another could be clipping, to cut and remove specific portions of raster image. Another can be the drawing and rasterization. Here, the process include to add vector graphics or text to raster form in a new image. That process is known as drawing and rasterization. So these are some examples of topological errors which might come up in raster format of data, and we have also discussed about the methods and measures which we can bring into our spatial information, and we may rectify the raster topological errors. Another kind of errors which might come with reprojection. It's a very important and interesting aspect of errors. In spatial information science, which involves modifying the projection of data set from one coordinate system to another. That is the process of reprojecting our spatial information. This is often necessary when integrating data from different sources, and these different data uses different coordinate systems. So the process can also involve resampling the data to a new cell size and defining a new origin. Another could be transformation. This is the process in spatial information science which is to calculate and used to convert the coordinates of data set from one geographic coordinate system to another. This ensures the data is properly aligned within a map. These transformation does not change the data, but adjustment is made into the coordinate values for proper alignment. The third and more commonly we do is generalization. It is a method used in spatial information science to reduce the detail in data. That process is known as generalization. This is often necessary when the level of detail in the data is greater than what is needed for the scale of the map being prepared. Now, this is required because, as we have discussed earlier also, that now in modern day in digital format, we have large volume of data. To just cut short the volume, we do sometimes generalization of the digital data. So this process is referring to that process, that kind of error which comes with generalization. But generalization can involve removing small details, smoothing out lines, or reducing the resolution of a raster. And in all these operations, the volume of data would be lesser. Each of these processes which we have discussed plays a crucial role in managing and manipulating spatial data in spatial information science. They allow for the integration of diverse data sets, ensure proper alignment of data, and enable the creation of maps that are appropriately detailed for their intended scale and purpose. But it may result in bringing errors. Another example is about when a study area extends across two or more map sheets. There might be small differences or mismatches between adjacent map sheets, as you can see in this diagram which we are showing. So, adjacent map sheets needs to be resolved, and this is known as, this process of error removal is known as edge matching. Normally each map sheet would be digitized separately and then the adjacent sheets joined after editing and reprojection or transformation or generalization. And as we have seen earlier, that these processes can bring in some kind of error. So that is to be rectified, and this process is known as the edge matching, where, as we are saying, that different data sheets, they would be recorded and bring into spatial information differently, separately. So then it might have some kind of errors which will come, and that error also need to be rectified, and this is another way of errors coming into the spatial information. Now, interestingly, there can be some intentional spatial information science data errors. Now, these errors can be intentionally introduced in spatial information science. And as we have discussed, these are more because of generalization. So, the data derived from different sources may have different coordinate system. The simplest method for generalization is to delete points between 2 points within a specified interval. You see, that process is known as the smoothing. If you look into the image, the top row of image, that gives you an idea of what smoothing means. But it will not preserve the space of the object. You recall we talked about vector data representation. So this is referring to that kind of vertices removal for generalizing or smoothing the vector data. When we generalize a map, some data loss is an issue, but it is necessary with comparison of different scale maps. Instead of this compaction technique could be used, it will help to reduce the space without any data loss. So these are some important generalization errors which comes. You see some other examples. For example, collapse. For example, merge. For example, displacement. Now, displacement would be to magnify the information. So these are important ways of generalization. The top row is collapse, where the small and minute details are being generalized. So these are some very important generalization process, but actually in some way intentionally we are changing the original spatial information for our convenience, but it is in some way is making some kind of errors, bringing in some kind of errors into our digital data. Just to conclude, it is essential to understand the always factor for errors in spatial information science data sets. And the inaccuracy, imprecision, and the resulting error can exist and come in every operation if appropriate care is not taken. And once in the data set, it would continue to inflate, multiply, and proliferate the subsequent operations analysis. So that way, these errors are very important and crucial. It is important to recognize that spatial information science data is always subject to some degree of uncertainty and error, and to take steps to minimize and account for these errors when conducting spatial information science analysis. This may involve multiple sources of data, validating and cross-checking data, and being transparent about any limitations or assumptions in the analysis. Simply because, as we are explaining it again and again, that once in the initial stage, if the data has some inherent errors, it will multiply subsequently when we would be performing some kind of analysis using this errors data. The use of metadata is one of the first tools that any spatial information science user should consult in order to know more about the data that he or she is using, and to avoid adding more error to a data that in any case will never be perfect. Any good metadata should always include some basic information like age of the data, origin, area that it covers, the scale, the projection system, accuracy, and most importantly the format, etc. So that way, when we look into the metadata, consult the metadata first, then we would have a better idea of the data which we are bringing into the spatial information science. And that helps us in minimizing the data errors in our digital data.